Hello everyone. So just like the last video on synchronous machine, today we'll try to obtain a DQ0 model of induction machine, and we'll try to investigate the different means uh, the similarity as well as dissimilarity of induction motor with synchronous motor, or rather synchronous machine DQ0 ref model. And at the same time I will left that means a steady state model of induction machine for you to means your last assignment, that obtaining induction motor uh, steady state model. And I expect that at least a few of you will submit the steady state model of synchronous machine as well as induction machine to me. And like the previous one, this time also, in order to save some of my and also yours time and data, I have written the equations on a paper, and then just using cam scanner I have a snap. So let us proceed. So we know that in case of a symmetrically means induction motor, balanced induction motor, that is, the windings are healthy and totally evenly designed. There is no means uh, all the winding parameters of all the three phases are identical, and you are going to apply a balanced voltage across that winding. And then if your winding is placed means spatially, if means the even means the spatial distribution of your winding is even in nature, then your winding is bound to produce a rotating magnetic field. While this rotating magnetic field, here you can see that this uh, theta ea, this first term, this theta ea is the angle measured from your a phase axis. All right. So a phase axis, this is the angle measured from your theta ea. So the total equation we can get it something like this. So this 3 by 2, we all are acquainted with this 3 by 2. Then the remaining term is like that 4.44 k omega, where k omega is our winding factor. Here, although I have not mentioned that winding factor, I just is consider this n. This n is actually k omega into n, because means mentioning k omega will complicate the overall understanding, right? So this is the stator mm, and we all know the omega sm, that is the mechanical speed of our stator rotating magnetic field. Please listen carefully, it's not the rotor speed, it is the mechanical speed, or that means you cannot realize this speed, or you cannot observe this speed, measure this speed from the outside, but your inside electrical means your electromagnetic field, your MMA, is rotating at a speed of omega sm, that is 2 by capital P omega e. This capital P is pole. Again I am telling you, capital P is pole, while small p is equal to, sorry sorry small p is equal to d by dt, right? Now we define sleep in our conventional way. Rest of the things are known to you, and similar to our synchronous machine case, here we will also define our this stator voltage equation. Here stator voltage equation, we can see the stator voltage, it is IAS, that is stator corresponding A phase current. RS here I have means I'm assuming that this RA is equal to RB is equal to RC is equal to RS, right? So as I have mentioned it that all the windings are even in nature, so you can understand, and this P is the differential of time differentiation of corresponding phase flux linkage, right? And similarly rotor voltage equation following the same means pattern or same uh, philosophy, we can write the rotor voltage equation also. And here one thing I would like to mention that in case of squirrel cage induction motor, this there is no need that you have a three-phase rotor. You can have, means let me write, n phase squirrel cage induction motor. You may have m phase rotor. Here for sake of simplicity I have just taken uh, means means equation where your stator and rotor, where stator and rotor both are having three phases, but don't expect that always. In case if you have four or say m number of phase in your rotor equation should be modified like and if the last phase is m, then you should continue till PMR is equal to IM RR IMR RR plus P lambda MR, right? This way you should continue and you should write all the m phase equation there. And needless to say here this uh, if we consider this matrix, this one, this is that what is the dimension of this belongs to and also this belongs to R6. In the case where you have m phases in your rotor, it may m may be greater than 2 or less than 2, but in that case you will have here, sorry, you will have it, dimension of this vector will be this 3 due to 3 phase of your stator, and these m are m number of rotor variables, right? And obviously when in the present case when we are having here R6 and here it is also R6, we can understand this transform means this inductance matrix, it becomes a square matrix, right? But in case this m is not is equal to 3, this will become uh, means rectangular matrix like we have observed in case of our synchronous machine, where we have intentionally considered one q-axis field winding G that causes an extra dimension in our rotor quantity or rotor vector. So this is all about, and here you can see this lambda a b c s. This is you are already acquainted with the definition of these vectors. These lambda a b c s, the three stator vector, three rotor vector. So there is nothing new to explain. And here one thing is important, that this L LS plus LSS means leakage plus self inductance, and all the diagonal terms are like this. And these LSM, these are the mutual inductance we are having here, as we have assumed that this machine is a symmetrical induction machine. That is why we are getting this kind of diagonal terms are, we can consider that of diagonal terms are equal, or means they are just having some even if they are not equal, but they are sinusoidally varying quantity with equal maximum magnitude. Now see here this LRR, it is we have got this. Now see the LSR, that LSR, here you can see this LSR, it is a matrix that is dependent on theta, and that is quite obvious that your the stator flux linkage will obviously depend on that this LSR, this relates stator and rotor. So it is a bridge between stator and rotor. So obviously it will depend on their corresponding or intermediate alignment, and that is why this is always dependent on theta r. Now here is the definition, that what is LSS, right? Mm, for sake of simplicity, I have not expressed LLS here in this equation. LLS is means kind of you can say it's a means actually LLS is a flux drop, means that effect we cannot get in our effective flux, so we should not means represent, and that incorporation of that will unnecessarily complicate the overall means understanding or representation. So SS, that is the self inductance of all the three phases. These are NS, where NS is your stator number of turn, and this PG is the air gap, right? As here this case is symmetrical, so there is no need to no, sorry, I made a mistake. This PG is not the air gap. It is the uh, permeance. Yes, it is the permeance. PG is not the air gap, it is the permeance. We know that if we multiply the number of turns with permeance, actually the unit of permeance is also Henry. So if we multiply that, we will get that. Um, and as we are having even air gap, that means that whole thing, if we see, it is even, like um, so although it's not even, but you can understand that this is an even case, so in case of even air gap, what I'm trying to see means show you here by drawing these lines. I'm not able to draw it correctly, but that this time some say here we are having two iron side, right, and we are having an air gap. So irrespective of the geometry of the air gap, your permeance depend on your material and the distance between them, right? So here that perpendicular distance always remain constant. So this total thing we can expect a constant permeance along this path. Similarly, when we have a kind of structure like this, right? Then we are having another structure. So this one, I hope you are getting my point that this structure, if we can have an even structure, it will give us an uniform value of Pg. Now, uh, that uh, and the same Pg is valid for your LSS and LRR. Actually, I will here I cannot draw it properly and it is consuming unnecessary time. I'll share a better video where we'll see how that permeance will vary with the intermediate distance, right? And also here in everywhere you will see it is PG, that permeance term remains same everywhere, right? Now here another thing you can see that this case matrix, we are all acquainted with this case matrix. This uh, Let me tell you two things. This omega is the speed of arbitrary reference frame, right? Omega is the speed of arbitrary reference frame, and your this omega r, it is a rotor speed. Better to say rotor electrical speed. Means this electrical speed is related to rotor mechanical speed, physical speed by this equation. Say, right? Sorry. Now here we are using the same previous matrix that we are acquainted with, that same element. The first one is for Q, second row is for D, and the third row is for zeroth vector. Obviously, here one thing I would like to mention further, that there is no such hard and fast rule that you have to use this particular case. You can have another case like this. You can have a case like with that first two row remain unchanged, like cos theta, sin theta. Only the last row should be changed by 1 by root 2, 1 by root 2, 1 by root 2. The first two row will leave this first two row unchanged, and the second row will be we should change it by 1 by root 2, 1 by root 2, 1 by root 2. And in that case, we may observe that case will become an orthogonal matrix, the new case. But here, this case is not an orthogonal matrix. Anyway, we are happy with our old and uh, means the first initial case, although that is not orthogonal in nature. Now, see here, one more thing, that uh, if we have to find it out, then we'll see the voltage equation from this two. The voltage equation can be written as is equal to, there will be a diagonal matrix like this is a diagonal matrix with all diagonal entries equal to RS. This is a diagonal matrix with RR. Here it would be like previous case IABCS, and here it would be IABCR, plus here you will have P on lambda ABCS and lambda ABCR, right? So this equation we have to use, and we'll get the, when we'll have to deal with that lambda ABCS, then this lambda ABCS, we know this will give this P lambda ABCS will get two terms, like can be written as P, here it should be right, and then you will have this lambda q d0s, your vqd0s you can find, and that will result plus rest of the term. plus rest of the term you will have. So we know that when we perform this, then it results as the one that we have shown here. All right, and means actually it will give you the two terms, means this one, this first term that is like our speed EMF, this this is our speed EMF, and the second term is like induction EMF. Fine. Now this is our means resistive drop. So we have these three terms. Now one more thing here I would like to say, and that is very, very important here in this context, that this PQT0S, it was transformation of your QD0S, right, that is rotating at a speed omega, and then you are again when this omega, when you are considering that time, you are, means your QD0 frame is fixed, means that is why you are getting this. And if you attach that QD0 frame with your rotor, then you will have an expression like this. Anyway, I will come to this later, right? Means what I'm trying to say, when you are talking about this was your stationary frame, stationary frame to reference frame. So what is the speed of your stationary frame? That was 0, right? Stationary frame speed was 0, and reference frame speed is omega. So basically this speed EMF would be written like omega minus 0. But when we are uh, dealing with the rotor quantity, rotor is not standstill. Do remember that when I used to means remind you several times that this is the sole reason that allows us to draw phasor of two different, apparently two different frequency signal on a same graph. If we see what is our phase, means stator frequency, it is Fs. Your rotor frequency is SFS, and if case of your motor is rotating, S is at least S, sorry, or stator is Fs, rotor frequency is SFS, right? As long as your rotor is rotating, this S is never is equal to 1. So Fs and is not is equal to Fr, not is equal to SFS. Fr is rotor, means uh, rotor electrical frequency. Now when we consider that rotor is mechanical speed, this Fs is the frequency of rotating magnetic field produced by your stationary stator winding, and this Fr is the frequency of your rotor winding conductor. But what is the physical speed of your rotor winding? If you can convert it in frequency, you will see that rotor physical speed is 1 minus SFS. So when you add this 1 minus SFS plus SFS, you get Fs. So what happened when you from level 0 you are transforming some to some frame, from standstill to arbitrary reference frame, still to arbitrary frame whose speed is omega, then here it would be like omega minus 0, because this is your stator uh, physical speed or stator winding speed in space. But when you are referring the same means this rotor quantity to the stator, then it should be, here I made a mistake, here it should be lambda, this term it should be lambda qt 0 r, it is not as lambda qt 0 r, and here also it should be like lambda qd 0 r. Anyway, the main thing that you should note, this one instead of omega as your that rotor on which your windings are placed, that is rotating at a speed of omega r. That is why the relative speed becomes omega minus omega r. Do remember that speed, that speed EMF is proportional to relative speed. It has nothing to do with the absolute speed of your winding, right? So likewise we understand everything and we can proceed gradually. And like in case of three-phase induction motor, here also, sorry, three-phase synchronous machine, here also you can see that the main advantage, here we can see that previously what was dependent, this lambda qd 0 is, it was previous case, if you see that lambda qd 0 is, when we are writing this equation, all these terms involve theta, and whenever we will try to find out p lambda theta, and whenever we'll try to find out something like so whenever we will have this kind of term like theta or theta plus 2 pi by 3, and whenever we'll try to find out p lambda, then all these theta dependent term will generate some dependency on omega, and that is no way helpful. So that is why here we can see that, like in case of synchronous machine, here we are getting something that is totally free from our means theta. But this is the difference between synchronous machine and induction machine. In case of synchronous machine, until unless you attach your reference frame with your rotor, the advantage won't receive is your transformation of from one reference frame to another reference frame won't give you much advantage. But here in case of three-phase induction machine, what would we can write that uh, transformation to any rotating reference frame will help us. Transformation to any rotating reference frame will serve our purpose, right? Now, in case of our this means another brilliant feature of this matrix is that they both the matrix are diagonal in nature, right? And also, if you have noticed one interesting thing, that the last component is zero. That means if you write the equation for a lambda naught is, that is the zero sequence component, it only depend on I naught is. It has got no contribution from I naught r. L naught is, L lambda naught is independent of I naught r. That is a very important observation, and this implies the your rotor winding can have any third harmonic current flowing through it. It won't disturb your stator winding, or vice versa. Your stator winding third harmonic current won't disturb your rotor winding. These two circuits are disjoint, unlike the case of means other q axis component or d axis component, where your lambda qs is dependent on iqs as well as iqr. But here this is true for zero sequence component, that is totally independent. And similarly here also we can see, like the previous case, that lambda q d0r, it is independent of I naught s. Lambda naught s, sorry, lambda naught r, lambda naught r is independent of I naught s, right? So that is a very important observation. So this is the total combined matrix here, and this lambda qr dot, lambda dr dash, lambda or dash, they are just following the transform formula. We can find out their value. They are just the rotor terms referred to our stator variable, right? Or stator means winding. So we have just observed that these can decouple, or means in our QD0 reference frame, that whole system is getting decoupled, and the zero sequence current of stator has nothing to do with zero sequence flux linkage of rotor, and as well as zero sequence rotor has nothing to do with zero sequence stator. But let us means I expect one question, but I do not know whether you will answer or not. But rather, let me answer, because that has to be answered before we proceed. That here, first question, that as we know that in case of uh, slip ring induction motor, sorry, squirrel cage induction motor, squirrel cage rotor circuit are short circuited. So for squirrel cage, obviously all these equation are equal to 0. VAR is equal to 0, VBR is equal to 0, VCR is equal to 0, just like damper winding of your three-phase synchronous machine. However, here without in, and we have analyzed synchronous machine in that way. But here we have not mentioned VAR is equal to 0. Rather, we are writing a particular equation. Obviously, that is a equation for RL series circuit. Whatever we have written for this one, that is a common equation for RL series circuit. That's is understandable, because the rotor circuit is also like stator circuit, comprises R and L. Fine. But instead of making VAR is equal to 0, whatever happens there, we are writing some equation. Why? The answer is that, as I have mentioned in your class, that we have two uh, induction motor. One is squirrel cage, another one is slip ring. The advantage of slip ring is that, in case of the second, the slip ring induction motor, this one, I'm talking about this one, slip ring induction motor. The slip ring induction motor rotor windings are externally available. Rotor windings are externally available. So at the same time, the rotor windings, we need to connect external resistance with that rotor winding, and that is the main advantage of slip ring induction motor. By connecting external resistance, you can vary our starting resistance during start, and once your means motor means um, once your motor starts rotating, then gradually you can cut down the rheostat, or means cut down the resistance, external resistance from your rotor circuit. And that is possible in by kind of online operation is possible, means you don't have to stop the machine and to means cut down the rotor resistance. During its operation, you can vary the rotor circuit resistance. That is a very big advantage offered by slip ring induction motor, although it is not rugged and means uh, like very compact. Means in case of squirrel cage induction motor, two phase, means main advantage is it is very rugged. There was no such electrical contact takes place inside squirrel cage induction motor, and therefore no electrical flashing also takes place. And another advantage, that squirrel cage induction motor is very robust, rugged, and very compact. But on the contrary, slip ring induction motor is not means design is not that rugged. It has got three slip ring to take your rotor windings terminals out for external means availability, and there in those slip rings means electrical sparking takes place, as well as this makes the whole system a bit fragile, and means it becomes a bit means not that compact like squirrel cage induction motor. So here the one and the most promising feature of your squirrel cage induction motor is that you can have a full control over your rotor resistance, and not only your rotor resistance, you can also control the voltage that is available across your rotor circuit terminals. Means rotor circuit terminal, we know that rotor circuit voltage is having a frequency SF, right? Now suppose if you can means uh, in your drive later on in fifth or sixth semester, you will read electrical drive, and then you will see that how This slip frequency voltage can be means reutilized, and means the scheme will be like you are absorbing power from your rotor circuit, and that is a voltage ASF, and that this by varying that rotor circuit voltage you can change the machine speed. I'm not going to detail in that. If time permits I can share one video on that also, but that is not our the present course. Can be we can proceed with our present discussion with this, but let me tell you one thing that here, so what we can understand that if our rotor terminals are taken out of the machine, means closed enclosure for our external means access, then obviously there is it is means not bounded to become zero. It is VAR is equal to zero or always zero. That is the case for only squirrel cage induction motor. But in case of slip ring, you can have a VAR is equal to VBR in case of balanced operation is equal to VCR, that is not is equal to zero, right? So I hope this just means discussion makes some sense why we are not making it zero, rather we are keeping the terms VAR, VBR, VCR, right? So let us proceed with this, and then we'll see here that we can have our whole model in terms of uh, means lambda QS, lambda DS, lambda not S, and here these three terms they are like referred to stator winding, nothing else. These three terms are referred to stator winding. So this means formula is very simple. Here you can see that it's just that ns nq are the means turns ratio, and also here one more thing, rather a slight connection I would like to suggest here, that these last three terms, it should be like I'm writing the total current matrix. The first three terms will be IQS, IDS, whatever, and last three terms will be IQR dash IDR dash I not R dash, right? Here I have missed the dash. Please incorporate this while means your uh, means discussion or means your analysis. Please yes, consider them. So just by using simple transformer relation, we can have our all these transformation, and here we can see that how ALM is equal to 3 by 2 LSSS, and all this means formula you can understand, and I'm not interested with the formula. Now very importantly, our power equation here, one thing I would like to suggest that if you consider squirrel cage induction motor, then you can drop these last three terms won't be there. But as we do not know that whether our machine is squirrel cage or slip ring induction motor, that is why we need to consider the last three terms of the first equation, because until unless we consider them, will that type of analysis will only be limited to squirrel cage induction motor. However, if we do this kind of generalized analysis later on, we can easily drop these three term without any difficulty, right? So this power, we know that this will be coming. How this is coming, that you are already means you should be familiar with this. And one important and interesting thing here, we must note that while we are talking about the speed voltage, that is very interesting that our VRQD is not R. I have already discussed. It is omega minus omega R, where omega is arbitrary speed. Arbitrary speed of what? Arbitrary speed of your reference frame. So this speed EMF always depend on our relative speed. This is relative speed, right? This has nothing to do with your absolute speed. Now here you can see this one, that this now one question may come in your mind, that how we are getting this result and how the things are cancelling out each other, that uh, without means solving them, let us try to figure out that how they are coming, these two terms. Let us try to find out them intuitively. See here, if we try to figure out, this is a cross term, means between d-axis flux and q-axis current, and similarly here it is q-axis flux with d-axis current. Now one thing you can recall, that when I was delivering lecture during your third semester, I used to tell you that when we are talking about the means flux that is acting in the same direction, either it will strengthen your magnetic field or weaken, but it has nothing to do with your torque production. Torque production can only be done by two, means flux and current. When these two flux and current, they are sinusoidal, means sorry, not sinusoidal, they are in quadrature, then only they can produce the torque, right? Means even if they are not in quadrature, then the means if we keep them uh, more close to 90 degree, we'll get the means higher amount of flux out of them. Means that formula we all know. I in my synchronous machine I already discussed. It is the simple BIL sine theta, and if you reduce theta from, means if your theta varies in 0 to 90 degree, and if you allow your theta to, means theta becomes small, then the whole torque will become small. So this Tm, the whole thing, this is very interesting. This means the basic thing what I'm trying to say, that two this flux and current winding, they are in quadrature, they are responsible for this torque production and this power transmission. So while we are talking about this torque production, this you can assume like this is our, means kind of air gap power. We can think that all these terms, they are producing some kind of air gap power, and we know when we divide this air gap power, let us denote PAG by air gap power by our synchronous speed omega s, or here we generally refer it omega e, then we'll get that electrical torque. So while we are writing this, see, this is also another interesting observation, that these two terms are equal. Now you may ask me that why these are equal? Because in case of lossless transmission, means if near ideal situation, if you see the air gap power, Let me write out Ag to denote air gap power released by stator is the same amount of air gap power received by your rotor. Fine. So